Hello, and thanks for tuning in to Microsoft Build. My name's Cosmos Darwin. I'm a product manager on the Microsoft Azure team. And in this session, we're going to be talking about shipping physical AI to the edge using a variety of technologies from Microsoft's Adaptive Cloud approach, including Foundry Local and Azure Local. Now, here's specifically what we're going to cover. First, I want to take just a moment to sort of frame the opportunity and the challenges of physical AI. We talk a lot about AI, including this week at Microsoft Build, but often it's in the context of like a chatbot on a computer screen. And there's so much more potential than that when we talk about bringing AI out into the physical world. And so that's what we'll frame up as the opportunity for this session. Then I'll show a demo of a sort of basic agentic robot to help you understand sort of the opportunity for combining language models and generative AI with physical systems. Then we'll spend most of the session unpacking how it works. I want to really give you a sense for some of the core ideas, what's novel and what isn't relative to conventional robotics. And then finally, I'll just very briefly mention a few of the adaptive cloud technologies that we used in this demo, including small form factor infrastructure, Foundry Local enabled by Azure Arc, and the Azure IoT Operations suite of platform services. Now, this session is for builders, so I'm not going to give you the marketing pitch for each of those products, but I do just want to give you a sense for how we used them to put together the basic agentic robot that we showed. OK, without any further ado then, let's get started. What is physical AI? Well, when we talk about AI, we talk a lot about the transformative potential, how AI helps so many people to really achieve more, to do things that they might have thought before would take a long time. Suddenly that time is compressed, and things that you would have considered to be a large, challenging task can be completed very quickly. But the benefits from those advancements have not been evenly distributed. Right? An awful lot of the examples we give are documents or spreadsheets, basically information workers benefiting from the advances of AI. Let me give you a few examples of types of work that have not really seen that same change. For example, performing inspections or maintenance or even repairs out in the physical world. This work has not really benefited from the advances of AI in the last few years. Similarly, factories, yeah, you can automate manufacturing in a factory context. A lot of things are actually built outside of a factory. You can look around and you'll see job sites everywhere where construction is happening, and you won't see a lot of robots, right? It's people performing that work. Similarly, in logistics and distribution and warehousing, a lot of this looks the same now as it did a decade or even 2 decades ago. Those gains in productivity have not really materialized yet. And those things, once they get distributed through logistics and arrive at brick and mortar retail or quick serve restaurants, a lot of the work of stocking shelves or food prep similarly has not really benefited from this advancement with AI in the last few years. So there's a common theme to all of these examples, which is that in each of these situations, interacting with other people and interacting with a changing environment around you, with changes in the sort of open world, is a core part of the work. And this is something that historically robots have struggled with. Robots excel when you're in a controlled environment. You're doing the exact same task over and over. So a factory is a great example of this. But all of those examples I just gave are domains where robots have struggled to make inroads. And as a result, the work looks an awful lot like it has for decades. However, what's exciting is that many people, myself included, believe that that is beginning to change. With some of the advances in recent years with AI models and being able to run them locally, it is possible to go from robotics to a more agentic approach to robots that may be better able to do a lot of these tasks. And so to illustrate that, my team and I have put together a basic example. Now, let me set expectations. This robot I'm about to show you, it's not going to take anyone's job. But it does serve to sort of show the potential of combining AI, especially language models, with physical systems. Take a look. Hey, robot, can you pick up the red cube? That's right, and put it in the bowl. Wait, I changed my mind. Can you give it to me? Thank you. Now pick up the green brick. Now put it in this green bowl. That's right, well done. Isn't the robot cute? Now look, as I said, it's a simple or a basic example. So that robot is not about to go out into the open world and address any of the scenarios I talked about at the beginning. But I do want to reflect on a few of the interesting aspects of what we just saw. I, as the person interacting with the robot, did not need to adhere to a strict syntax of commands or to sort of start or stop the robot. I could interact with it in a very natural way, in a very fluid way. I could just say what I wanted it to do, even if it was a kind of rambly sentence. Hey, robot, please, would you mind maybe picking up that thing there? And then the robot, because it's an agentic robot, is able to reason about what it heard and figure out what I meant anyway, even though, the interaction was kind of messy. The inputs coming from a person were messy. And likewise, it was able to respond as the environment around it changed, because it's continuously listening, continuously looking, and when I moved objects on it or when I changed the instruction midstream, it was able to sort of pick up and adapt and keep going. And so you can easily imagine a version of that with a different embodiment, more sophisticated hardware, for example, with more different things that it knows how to do, being a helpful collaborator in spaces where historically people have not been able to benefit from having a helpful robot collaborator because of the challenges I mentioned. OK, so how does it actually work? Let's unpack a little bit what is going on behind the scenes in that demo so that you can see the pieces that are new and novel, and then the other pieces which actually are very much just sort of conventional robotics. Everything you saw in the demo, all of the intelligence required to make the robot work as shown, runs on this small industrial computer. For the demo, we used a Lenovo ThinkEdge SE100 because it's sort of industrial grade. It has an optional NVIDIA discrete GPU, but many other devices would work too. This is just the one that we chose. This computer is physically on the table, co-located with the robot. You can see it actually in the background of the video. And it's connected just over USB, nothing fancy, to 3 peripherals. First, a UVC-compliant RGB camera, which is positioned over the workspace, looking down at the table. Second, a UAC-compliant omnidirectional microphone, which of course is used to capture the speech. And then finally, the small tabletop robot arm, which has 6 degrees of freedom and a 7th if you want to count the gripper attachment that it has. By the way, all of these are deliberately kind of approachable, off-the-shelf budget options, because there's very little preventing you from just trying this at home yourself, as we did. Now, in the video, you can see each of these things, but just to sort of show you clearly, that was the USB camera over the work surface, and that's the USB microphone. These really are there's nothing terribly fancy about these. It's not a depth camera or anything like that. It's just a classic, almost like a webcam. So that's the hardware setup. Perhaps a little more interesting is on the software side. So on that small form factor industrial computer, we chose to run the Azure Linux operating system, and then Foundry Local, which you may know as something that was originally available on Windows, then it expanded to Windows and Android. Foundry Local is now newly packaged as a container image that you can run on Linux, which was a great fit for our scenario here. And Foundry Local then hosts all of the AI models that we use to make the robot do what it does. So at runtime, here's how this actually comes together. Firstly, audio from the microphone is split into utterances and then fed into Nemotron speech streaming. Nemotron is a speech-to-text model that is developed by NVIDIA. It's available for free in the Foundry Local catalog, and it's great. It's one of the best models in terms of performance and in terms of very low error rate. So as you saw in the video, even though I am facing away from the microphone, not speaking terribly clearly, there's a bunch of ambient noise, it was still able to pick up and transcribe everything I said very reliably. And so feeding the audio into Nemotron speech gives us back text of what was said by the user. In parallel with that, frames from the camera over the work surface are continuously being captured and fed into a variety of vision models, including an open vocabulary detector model, to recognize everything that we can see on the surface. So that certainly includes colored blocks and the little bowls or containers that we put them in. It includes a human hand, for example. But it's not limited to that. Something we didn't show in the video is also just everyday objects can be recognized by these detector models. So like sunglasses, for example, or a wedding ring. That's no problem. It will pick them up. And basically, for each of these detections, it's returning the coordinates within the frame of where that object was seen. And as applicable, it also returns the orientation, the major axis of rotation, because, of course, that's very important if the robot is going to go actually pick that object up. So the vision pipeline gives us these coordinates and angles of rotation. Now, for the most important part, the reasoning. So all of these inputs, the text from the speech pipeline and the coordinates from the vision pipeline, are fed into a small language model that runs locally on that small industrial computer. Now for the demo, we chose 𝗦𝗲𝗀 because it's available for free in the Foundry Local catalog, and it supports reasoning and tool calling. But many other options would likely work as well. We chose the 1.7 billion parameter version, which most people would say means it's a small language model. But if you had more compute available, you could also run a larger version and quite possibly handle more complex types of instructions. So what's happening here is, given all of the inputs, the language model is asked to choose between a set of tool calls that are available to it. Now, for our example, again, it's very basic. It's very simple. We just gave it 4 tools that it knows how to call. Those tools are pick, so go pick up an item at a location. Place, put it somewhere at some other location, or pick and place, all as one movement. And then the final tool call is stop. So when it hears something like in the video when I say wait, right, it interprets that as a stop tool call. And so all the language model does is decide, based on what it sees and hears, which of these tools is it being asked to call. And in the example we've been using, of course, it's a pick and place tool call where the pick target is the red cube, the place target is the hand, me. And once it has done that interpreting, the rest is pretty straightforward, right? That gets converted into a sequence of movements that get planned out, and then the robot arm executes them. This part is really no different from how it would have been in the past. What's so interesting is the additional flexibility, the additional almost humanness that comes from the robot being able to interpret very messy inputs and still figure out what you meant and then complete the task if it's among the set of tools that it has. All right, there were a number of adaptive cloud technologies that we used to make this demo possible. And so I do want to just briefly touch on each of them. The first one is the small form factor infrastructure, that industrial computer that we used to run the whole demo. There are a bunch of capabilities that Microsoft Azure has offered for several years that have previously been limited to Azure Local on big servers. This is things like provisioning machines from the cloud or managing them from the cloud. What's new is that those capabilities are now available in preview for these smaller industrial form factors. So take a look. In the Azure portal, I can go provision a machine. And you'll see when I input the ownership voucher for that Lenovo SE100 that I have, it picks it up. And I can actually choose what software stack to install onto this computer straight from the cloud portal without needing to plug in a keyboard and monitor. So in this case, I chose Azure Linux, and I could do that provisioning entirely from the cloud. Once I do that, I get a resource representation in the Azure Resource Manager for this computer. And you'll see it looks and works an awful lot like a cloud virtual machine. It's a provisioned machine resource type, and it has a bunch of things that I get visibility into and management functions that I can perform. So one simple example is I can grant access to this machine to a colleague of mine directly from the cloud portal using Microsoft Entra ID, which means I don't need to have like a password on a Post-it note that I've written down or an SSH key that I send to them. This is a much more robust way of managing a device like this, which is going to be really important if I want to take this system and have hundreds or thousands of them distributed across many locations. Being able to manage it all through the cloud control plane is going to be extremely helpful. So that's one of the things that we did in this demo. Another one, which I've already mentioned, is we used Foundry Local, and specifically the flavor of Foundry Local that is newly available now as a container image for Linux. So on our small form factor industrial computer, we installed Azure Linux, as I said. Now, also to keep all of this straight, we also just installed a K3s, like a small single node Kubernetes. And then we packaged our application code as a container. Now that code is just Python. It's really not terribly fancy. But alongside that container, we then deployed Foundry Local in a container. And Foundry Local exposes an OpenAI-compatible REST API that we can use to make inferencing requests. And this is great because it means we don't need to host the AI models in our own code, which can be very clunky. It can you can run into challenges related to like size and agility and all sorts of reasons that you don't really want to do it that way. But also, there are a few specific advantages of this approach that I thought were pretty compelling. The first is Foundry Local gives you a trusted, authoritative way to access like a safe instance of a model. And so in our demo, we wanted 𝗦𝗃, the 1.7 billion parameter version. All we had to do was give its name in our configuration file, and then Foundry Local goes out and retrieves a trusted copy of that model from the Foundry Local online catalog, downloads it to run entirely locally, and from that point on, there are no calls to the cloud at all. It's just running inside of that Foundry Local container for you. And you can see in the catalog here, there are so many options available, including Nemotron Speech, the other model that we used in the demo. Once the model is running, you can then just access it using an endpoint very much the way you would if it was running in the cloud. It's like a drop-in replacement for making an API call to a public cloud. Instead of accessing, say, Azure to run the model is running locally on the small form factor device right next to your code. What's great about that, of course, is the latency is super predictable. And for a system that is going to be out in the physical world, interacting with people, it all needs to be as close to real time as you can get. So this is a great fit. Now, speaking of real time, the other thing that Foundry Local takes care of that I loved is it handles detecting the available hardware accelerators in your hardware and lighting them up for you. And so in our case, our Lenovo SE100 has an NVIDIA GPU. It has an RTX 2000 in it. And when you're using Foundry Local on top of the small form factor infrastructure managed through Azure, the whole top to bottom stack can be lined up for you. And so everything from the kernel mode driver to the device plugin to the user mode libraries that are inside of the Foundry Local container, all of that is lined up. And actually, as you see in the diagram, your own application code doesn't even need to do anything with the GPU, actually. And you're still benefiting from GPU accelerated inference because as you make those inference requests to Foundry Local, they happen much quicker because the GPU is there. And so in this instance, it sped up reasoning by 𝗀 by a factor of many times. We tried it both ways. This was a huge boost. Here you can actually see a screenshot. This is a pre-release tool, so it may change a little before we release it. But you can see a screenshot of that NVIDIA RTX 2000E running in our device. And in the Azure portal, I can see the usage of that GPU. So every time 𝗀 is asked to interpret some instructions, you can see a small spike in the GPU usage, which shows you that it's being used. All right, the last piece of the puzzle I want to talk about is Azure IoT Operations. IoT Operations is a suite of platform services that enable you to connect to devices and protocols in your local environment, and then connect the data from them up into the cloud and potentially route commands back, such as mission plans for a robot, for example. IoT Operations includes a number of built-in connectors that are really handy for things like OPC UA, HTTP, unveil, and it also includes an industrial-grade MQTT broker that you can configure so that as data flows into the broker, you can then configure how it gets transformed and sent up to the cloud, for example, for you to do analysis in Microsoft Fabric. Now, in our example, there are some things that we were interested in monitoring. One of them is the robot's span or reach, right? Our robot, of course, is very small, and it can only reach, I don't know, maybe half a meter or something. The field of view of the camera is actually larger than that. And so occasionally, you have the situation where the camera can see an object, and the robot believes that it's being asked to go pick or place that object, but it actually can't reach it, as you see in this image here. Now, in the case of just a single robot on a tabletop, of course, it's not that hard to diagnose this yourself. But you can imagine deploying this across many locations in the field. Being able to get real-time telemetry and intelligence off of a system like this is everything. And that is where Azure IoT Operations is so valuable. Let me show you. So on the K3's instance that we run on this small industrial computer, we deployed Azure IoT Operations using the extension approach. So both IoT Operations and Foundry are available as extensions, which means it's just a couple of clicks or a single YAML file, and you're off to the races. Once IoT Operations is installed, you get this really approachable operations experience, which would be usable not only by a more IT persona, but actually an operations persona who maybe has specific knowledge about millimeter offsets and things like that. And so you can configure how data should flow from a discovered asset in your environment, in this case the robot arm, up into a workspace in the cloud. And you can even transform that data here. So for example, if you needed to do a unit conversion or add or remove additional properties, like in our example, we're just trying to see if the coordinates are safe to reach. For example, we could remove the z coordinate because it doesn't really matter here. And you can do that through this very approachable interface so that when the data arrives in Microsoft Fabric, it's ready for your data team to just interact with. It's already cleaned up. It's already formatted in a way that they'll understand. And so for us, we configured Azure IoT Operations to stream all of the coordinate requests from the robot. So every time that it is asked to go grab something at a particular location, it streams back what coordinates it was asked to grab from, and we can then analyze if those were safe or unsafe. And all of that is coming in real time off of the system. So you can imagine if you were going to deploy this broadly, this would be an extremely valuable capability. OK, so where does that leave us? Advances in AI, together with Azure's Adaptive Cloud approach, are making it easier than ever to build and operate intelligent physical systems. This year, and I think in the years ahead, we are going to have to update our notion of what types of tasks it is possible to extend AI to with an agentic approach to robotics. If you're as excited about this as I am, I encourage you to get started right now. All of the things that we showed here are available off the shelf for you to try. The small form factor infrastructure is available in preview now. You can take it for a spin. Foundry Local as a container image for Linux, enabled by Azure Arc, is also available as a preview right now. You can go try that out for a scenario like ours or many other scenarios as well. And of course, last but not least, Azure IoT Operations is also available for you to try. All right, that's it for me. Thank you so much for watching, and enjoy the rest of Build.